So welcome to Aerospace Structures 1. Today we'll be covering the failure modes of structures. And in today's lecture, what we want to discuss is the types of failure modes that can occur in launch vehicle, spacecraft, and launch vehicle applications. And a motivation I want to provide to you in today's lecture is the aircraft Boeing 777X. The fuselage of the 777X ground test airplane was split by a high pressure test. So typically, when you're trying to fly an airplane or a launch vehicle, and you want to deploy that to your customers, typically you have to do a qualification test. A qualification test will take the design and test it to the limits of that structure. And so the high pressure rupture test is one such test. In this case, the wings were bent upward, and while the interior cabin was pressurized. That's one of the combined load conditions we'll be discussing later that need to be considered in the qualification testing. And during that qualification test, it was found that the test hardware failed as it was approaching the target stress levels, and an explosive depressurization occurred during that event. And a passenger door blew out and fell to the factory floor. What I want to say here is that you want to avoid expensive failures like this during the test program. And you want to avoid these kind of failures during the production phase and operational life. And that's why analysis is so important at the beginning of the program. You want to make sure that at the beginning of the program, the analysis has considered all the different failure modes that may occur. And the reason you want to do that is because you don't want to have an expensive failure like this one. The issue is that trying to foresee every failure mode in advance is just not very feasible all the time. And so that's why it's so important to perform a survey of all the failure modes that could occur and making sure as early as possible in the design process that you have precluded all these failure modes that could happen. So that's of very high importance. And so that motivates to this lecture. Today's lecture, what I want to show you is all the failure modes that could occur in these applications. Many structural failure modes exist in aerospace structural applications, and so that's why we want to be able to identify those early in the design process. The complexity of failure modes and the actual failure modes will also depend on the material selected. Aerospace structures have to be designed to meet the structural performance requirements and to ensure that the structures are robust against the several failure modes. And so that's why you want to get material properties and test data as early as possible, because if you don't, you're going to run into a problem. You're going to run into failures late in the program, which could cost millions of dollars. And what we want to do is avoid these expensive failures. It does require significant experience, and it does require significant amount of engineering judgment to balance cost, schedule, and technical risk. And so it is important then to ensure that you do spend the money ahead when you're doing smaller tests, because the smaller tests are less expensive. You want to balance that with also moving quickly through the program, because you don't want to be spending years doing small testing, but not scaling that up to the larger tests that need to occur. And so, yeah, so what I want to point out also is that structural failures do occur for a variety of reasons. One of the reasons is that the hardware may not be properly qualified by test or analysis. You thought that the hardware was qualified to the low levels it will experience in service, but then you did not really account for the test like you fly differences. When you fly and when you test, you're going to see different conditions. You cannot test everything on the ground. For example, an airplane, when it flies, the boundary conditions are quite different from when you test them on the ground. For example, on the ground, I cannot test it to the ultimate conditions on the ground. It is very difficult to do, to test every single condition you're going to see in flight. So you're going to have to make some assumptions about those conditions between test and flight. And those ground testing that need to occur need to really consider all the types of differences you're going to see against flight. As a consequence, you still have to do a test flight. And as a consequence, when you go to production and you now have airliners flying the airplane, there's still the potential for failures to occur because your analysis and test may not have been perfect. And so in many cases, if a failure occurred in flight, it's because in some cases the hardware was not properly qualified on the ground. Does that make sense? And so we want to make sure that the flight loads also do not exceed the structural capability in flight. You know, so you could design the aircraft or launch vehicles to a particular set of load levels, flight load levels. But there might be the case where the flight loads that were used in the design are just not good enough. They should have been higher. So maybe in service, the flight loads were actually higher and the flight loads were actually underestimated. And so as a consequence, your testing will have been done at lower load levels. And then when you go to flight, since the flights will be higher, potentially because it was not characterized, fully characterized, then there might be a problem. And you could have a failure by material overload, which I'll be discussing later today. Hardware defects could also be caused by known or unknown manufacturing issues. Unknown manufacturing issues could entail delamination. I'll be covering that. For example, in this scenario, you have a composite sandwich structure that has core that's uneven. And that core is going to cause a mismatch height in the composite, outer mold line. Visually, you will see that as a dent in the composite. Well, guess what? That is a non-manufacturing issue. But if the hardware defects was such that this height, mismatch height was too large, and it could cause a significant amount of degradation in strength, then it becomes an issue. And so you want to make sure that any hardware defects are accounted for and are analyzed to and tested to ensure that the hardware defect will not become a failure point in service. Unknown manufacturing issues can also occur. I could have a defect that's hidden in the structure that I probably didn't know about. That can be a significant problem because I'm flying something with basically a hardware that has a significant amount of potential for that hidden damage to get exposed during flight. And you don't want that to happen because that's basically a very, very concerning scenario that could result in the loss of life. Hardware damage due to handling or transportation is also quite important. For example, I could have a composite sandwich structure as shown here, and the core is subjected to a crushing load from an impact damage event from the outside. Well, that crushing damage could cause a delamination shown in blue of that ring shape that you see. And guess what? A delamination shape of this type could cause up to 60% strength reduction. The scary part is that if you looked at this composite sandwich structure in person, you will see that that hardware damage was not visible. And it was very hard to see. Yet, when you were to go and test that hardware, which had the impact damage event, and the only image that shows that damage is a ultrasound or a non-destructive evaluation technique looking at signs of damage, if you were to do a test, the strength reduction is just too high. And so that's quite concerning when it comes to the use of composites, and I'll be discussing that later today. The lesson learned that I really want to pass along to you is very simple. Do not forget the lesson learned. That's the lesson learned. And the reason that's a big lesson learned is because in the aircraft, launch vehicle, and spacecraft industry, there's a number of failure modes that occur. And when you go to the next design, we forget the heritage learning experiences that we had in the past. And so those lessons learned don't get transmitted moving forward. And so you can repeat those mistakes again. And so carelessness in the design, production, and operational phases can also cause structural failures. Unit inconsistencies, swapping an adhesive system to an unqualified one that could look similar, the adhesives could look similar, and they were swapped, but one adhesive system has a lower strength performance than the other one. Cutting corners in the design, that could be a problem. On 23 July 1983, Air Canada Flight 143, they ran out of fuel about halfway through the flight. And the reason was because the fuel loading was miscalculated through a misunderstanding of a recently adopted metric system. So for that trip, the pilot calculated a fuel requirement that was completely different from what it actually really required. And so that's just one example of carelessness. It's just one example showing that we're humans. There's nothing wrong with being human, but it's important that you understand that the design of spacecraft, launch vehicles, and aircraft, paying attention to details can save a lot of people's lives. On September 23, 1999, NASA lost a $125 million Mars Climate Orbiter spacecraft after many days of the journeys to Mars. The miscalculation that came into play here was the use of English units instead of the metric units, and that got them to set a course that was 60 miles away from where they needed to go. And the issue here is that it was inconsistency in the units. The time Lockheed Martin, which was performing the calculations, was sending thruster data in English units to NASA, while the NASA navigation team was using the metric units. What I want to point out here is that anytime you're working on any problem, and I don't care what problem you're working at, thermal, moisture, fluid mechanics, structural mechanics, or a combination thereof, I think it's of high importance that you make sure that your units are consistent across the various disciplines that are involved. It's also important that you pay attention to detail, which is the main message I'm trying to get across in this particular slide. We also have structural failures caused by dishonesty in purposefully trying to hide technical rigor in exchange for cost savings. And that is a problem that is encountered in industry. That fraudulent behavior can cost millions of dollars, and it can cost people's lives. You could also inaccurately characterize the material properties. You can get the wrong properties, and that can be a big problem. You could also have the incomplete identification of all the potential failure modes. And in addition to that, there's the unknown unknowns. You know what? You tried everything you could. You put all the effort you could. And everybody did everything they could in their power to identify all the failure modes. And yet, a failure happened during test, or a failure happened in flight. And those are scenarios that we just cannot do anything about other than trying to do all the right things ahead of the game. And those scenarios are perfectly acceptable. Unknown unknowns is where we learn the most, because now those unknowns become knowns for the future. They become the lessons learned they can now apply for future applications. The other thing I want to mention about unknown unknowns is that unknowns unknowns can become also a crutch. It can become an excuse of not trying harder. So it's important to understand that unknown unknowns is there, but it's not something to lean against to say, well, I don't know what's going on, so that must be an unknown unknown. No, you want to make sure they've done all the homework and they have characterized as much as possible. They have identified all the failure modes, and your teams have worked hard enough to ensure that all the failure modes have been completely precluded and that we won't see that in service. That's just extremely important for you guys to understand. Structural failures also occur due to manufacturing errors, such as improper heat treatment. You chose a wrong heat treatment that caused the metals to have lower strength than what you had required in the design. You could have the incorrect surface finish. The surface finish during the test program could have been a very nice surface finish with very little roughness of the surface. Yet later in service, the surface finish becomes worse over time due to process controls that are getting lost. Well, guess what? A rougher surface finish can cause a crack initiation a little bit earlier in service, and perhaps that crack initiation can now drive a failure mode that was not foreseen before. Manufacturing errors can also include thickness variations that are outside of the drawing spec. Processing can also affect the strength and corrosion resistance. We could also have situations where we have assembly errors. You could have the incorrect torque, the incorrect sequence of how everything is getting put together. You could also have the situation of omitting or adding unspecified components. And so that those assembly errors can be problematic in the life of the program, and it's important to understand that they need to be considered in the design, production, and life phase of that particular component. Hardware is also can be exposed to adverse environmental conditions, whether known or unknown. And I'll go through some of those examples, but salt environments can cause corrosion as an example, and that's an environmental condition that can be a problem. I'll go through that in a little bit more detail as we move forward. You also have normal wear, such as fatigue, fracture, and creep, and these are areas that occur when a structure is in service for a long period of time, and those need to also be considered in the design process. You also have the situation that discussed earlier where you could be using unapproved parts, and that's where dishonesty could be a problem. Or maybe it was not dishonest. Maybe it was not known that those parts need to be approved by the aviation authority. But parts manufacturing without an aviation authority approval, we are typically describing those as not approved. They may be inferior counterfeit. They could be used beyond expiration dates, such as adhesive systems or composites, which could have an expiration date. But because you didn't want to spend more money, you went ahead and continued using them to save money. You could also have situations where the parts are untraceable, and that could now add a problem. The parts are cheaper to buy and more profitable to sell than approved parts, and that's part of the reason, motivation of wanting to use unapproved parts. Unapproved parts also have been found on both civilian and military aircraft, and faulty ones have caused many accidents and incidents that have cost people's lives. So again, that's why honesty, integrity starts today. If we cannot be honest today, then that behavior will carry forward into the professional industry, and your actions could cost people's lives. So it's so important for you to really pay attention to detail, number one. Number two, to ensure that we're taking the actions for the right reasons. If I'm going to fly an airplane that I know has an issue with the thickness of the skin, and I know that smaller thickness could be a problem, you should speak up. You should bring this up, because actions can be taken. While they might be costly in terms of money, they could save people's lives. And not always those actions of bringing them forward will be a problem. Sometimes those actions can be resolved by repairs that are not expensive. And so it is important that engineers speak up when that happens. An example of unapproved parts or issues with this type of behavior is on February 24, 2009, the Towers XL rocket launched from the Vandenberg Air Force Base in California. And it was carrying a NASA satellite designed to measure the carbon dioxide levels in the atmosphere. But the payload never really properly separated from the rocket. And that was a real problem. The mission was lost. In March 4, 2011, we again had the same situation, but now carrying a NASA satellite. And it was found through extensive investigations that faulty aluminum extrusions used in the mechanism by which that payload separates from the rocket, and that portion of the rocket where the separation occurs is called a frangible joint. And that frangible joint did not work as planned. It prevented the separation from occurring. Well, investigations into the suppliers found that the company had falsified records about the material used in the extrusions for about a decade. And they found accounts internal to the company showing that material property tests the results were altered, alterations were made to the test results between 1996 and 2006. And so this shows how dishonesty or falsifying information or not being careful could cause a significant damage that could kill people or could cause science missions or expensive satellites to fail. So what is a mission statement? Anytime you work on something, I encourage you to come up with a mission statement. What are you trying to achieve in what we're trying to do? What we're trying to achieve here is to ensure the structural integrity of aerospace vehicles, and that the integrity of these vehicles be maintained throughout the phases in flight with the least amount of cost, with the least amount of schedule impact, but with the most technical rigor we can achieve. Structural assessments are highly challenging. And why is that? Because, think about it. These are flying buildings, right? Designs and failure modes are quite complex. And I have to make them light. I have to make the structures light. They can't be too heavy because otherwise I can't fly them. And if I fly them, then maybe the payload that I'm putting there is just not going to be able to carry as much anymore. So the designs in general carry very low margins for weight savings purposes. And yet you have this design and failure modes are quite complex. The designs are subject to highly complex launch and ascent environments. And on top of all that, when you make the hardware is not perfect. The hardware is going to come. Nobody's perfect. When somebody makes hardware, the hardware is going to come with defects. And the defects may not meet the drawing requirements. So if the thickness in the drawing was 30, plus minus 30 inches, there is a situation where the thickness could come even lower. What are you going to do in those scenarios? So the defects in the hardware not only combine with the lower margins that the system has, it combines with failure modes that are complex, and suddenly here you have a challenge in your hands. So this requires for us to understand the type of failure modes we will see, and we also want to learn how materials fail. And as we've discussed in the first lecture, hand calculations are extremely useful to predicting failure. But as the design matures, it's of high importance to start refining those models with high fidelity models, also called finite elements, to start to reduce mass, but to yet make sure that I haven't reduced it to the point that I cannot accommodate defects in the hardware, and I cannot not accommodate drawing tolerances. So it's very important then, as a designer, to carry additional pocket margins in your pocket. I don't want to design something with no margin. I want to design something with some margin. So when somebody drops a tool, or there's an issue with the thickness of the part, that I'm able to make some important decisions that are not going to cost me a lot of money. They're going to allow me to eat into some of that margin that I was very smart about keeping in the design phase. And I can use that margin and apply towards these defects that are occurring. And that way I probably can accept that damage without having to redesign, having to repair, and so forth. But you don't want to keep too much margin to the point that your structure is too heavy. And so therefore you're unable to, basically you're unable to fly the part because it's too heavy, right? We don't want that situation. A big lesson in the design of aerospace applications, launch vehicles, spacecraft, and airplanes is to keep a simple design. Keep a simple manufacturing process and ensure that design is analyzable. Make sure that you can minimize the number of failure modes in the design as well. So some important lessons learned, I think, are very important to pass along to the team, is that it's very dangerous to assume that you will have a defect-free structure when you're looking at the safety of flight components. You just cannot assume that everything is perfect because defects are bound to occur. Critical parts and potential failure modes must be identified early in the development and program, because you want to put some controls to capture those failure modes. We also want to identify fully all the environments you're going to see in service. The structure is going to experience perhaps thermal, static, dynamics. In this case, I'm talking about an engine, but it applies to everything. It applies to every single piece of structure. You want to make sure that all the thermal and static and dynamic loads are fully known. And if you don't know them very well, you want to put a factor that envelopes the loads. Some important lessons learned is that it is dangerous to assume that you're going to have a defect-free structure, especially in the safety of flight components. And the reason that's important is because when you manufacture a part, it's rarely going to be the same as a drawing. And you're going to have flaws in the structure. Critical parts and potential failure modes have to be identified really early in the development program, because if you don't identify those failure modes in advance, you won't be able to apply proper controls down the road. And what I mean with controls is when you're designing something, you have to come up with the design space. And so you have to put controls into the design space so the structure that you end up designing is fully robust to against the failure modes it may see in service. Here in the third bullet, I'm discussing engine development, but this applies to every single structure you may have. You have to identify all the environments, thermal, static, dynamic. All these environments need to be fully characterized, because if you don't characterize these environments, the issue is that you're not going to be able to design a structure to be robust to these environments. For example, if I forgot that this particular piece of structure is going to experience 300 degrees F, and I only design it for static and dynamic loading, and that 300 degrees F causes a strength reduction in the structure, that is a major problem that needs to be addressed. And so another lesson learned is that complex components require analysis, and this analysis should be test validated. Anytime you're working on a component that has a lot of moving parts, or the joints are quite complex, and hand calculations are okay, but you don't have certainty in these hand calculations. In those cases, it's important to perform testing, subscale testing, not the full-scale testing of testing the whole aircraft, but testing portions of the aircraft or launch vehicle or spacecraft. So you don't spend too much money failing a large-scale composite or large-scale airplane. You can use those complex level testing at the smaller level to validate this analysis that can then be used to analyze the actual full-scale design. The analysis is actually very important. It connects testing to flight conditions. And that's where analysis can help, is to evaluate the differences between the test conditions and flight conditions. Materials and processes should also okay, so can you hear me? Materials and processes have to be adequately characterized. You also want to make sure that we have the fluid structural and structural interaction well characterized. So the fluid is going to interact with the wing, for example. We want to make sure that that's fully characterized. In a launch vehicle, you may have the fluid inside a tank slosh, go back and forth, and interact with the structural modes of that stage tank as the launch vehicle is flying. You could also have structural to structural interactions. For example, the engine vibration environments in an aircraft could interact with the fuselage. And so you want to make sure that those interactions are well understood. Another example is a spacecraft application. A spacecraft is attached to a launch vehicle, and the launch vehicle vibration environments could be quite severe. So I want to make sure that the structure-to-structure interaction, which in this case is a launch vehicle interacting with the spacecraft, does not cause a problem to the spacecraft. And finally, another lesson learned is to ensure that you have managed procedures to ensure that you have realistic expectations for the team, you have realistic inspections, you have maintenance requirements, and you have good configuration control. You want to make sure that you're not changing a part to save money and not tracing that change, because perhaps that change was adverse to the structural performance that we're discussing here. And so let me dive into the failure modes we'll be discussing today. Overload, such as brittle and ductile failure modes, are examples of that. Excessive deformations that can impact functional performance, that can involve yielding, elasticity. Even elastic deformations can impact functional performance. If you have a loading condition in a structure where a particular part deforms too much and that part interferes with the functional performance of another part, that can be a problem. And so you may have to increase the modulus of that part so when that part deforms, it does not impede that functional performance. You also have dimensional instability, and dimensional instability can also be a issue when it comes to deformations. And I'll give examples later when it comes to the coefficient of thermal expansion. You also have general wear of the structure. You're going to have fatigue, cracking, creep, relaxation, wear, abrasion, and fretting. And I'll dive into some of those examples as we move along. Environmental conditions such as stress corrosion cracking, corrosion, high temperature corrosion, hydrogen embrittlement, hydrogen-assisted cracking, and oxidation. These failure modes are caused by exposure to environments, and they can be causing hidden failures that you may not be aware of. And so these failure modes really need to be taken into account during the design phase to ensure we're not missing these failure modes. We also have thermally driven failure modes such as CT mismatch, thermal shock, melting, and erosion. Failure modes from impact damage can also occur, and we'll be covering that, and also buckling and crippling. What are the types of failure modes that could occur at the system level? You're going to have failure modes that are very specific to metals, to laminated structures, sandwich structures, and failure modes are specific to bonded joints, mechanically fastened joints, and weld joint designs. There are also failure modes associated with a high temperature material. The use of high temperature materials in nozzles or re-entry vehicles. Those are going to have very specific failure modes you may not see in other applications. Not all failure modes here were cataloged, but they show the percentage distribution of the failure modes that could occur. You have corrosion environments occurring for quite a significant portion here. You also have fatigue, brittle fracture, overload, and corrosion examples and creep examples. And there are examples of, many examples for each of this. This source is where I got this from, why aircraft fail. But there are many examples of each of these, and I'll go through some of those examples so you're clear about why failure modes need to be considered in the design process. One of the things you want to do as a designer of an aircraft, spacecraft, and launch vehicle is to really catalog all the different failure modes that have been seen in the past and making sure that those failure modes are considered moving forward, because there could be a scenario where those failure modes could come to bite you because they were not considered. Here are examples of failure modes that are cataloged by initiation site, and it shows the percentage distribution of the failure modes that could occur. This chart also came from Why Aircraft Fail. And you can see here that for fixed wing like aircraft or helicopter design, the failure initiation sites range from bolted areas, stress concentrations such as fillet, radii, sharp notches, weld locations. Welds are very notorious for having high variability. Corrosion, threads other than bolts or studs, manufacturing defects or tooling marks, scratches, nicks or dents. Scratches, nicks, and dents are very common, and they can become stress concentrations that could then initiate a flaw on the fatigue applications and then propagate during time. We also have fretting, surface or subsurface flaws, and we also have improper heat treatment. We can also have maintenance-induced cracks, and we can also have wear failures. And you can see the comparison of failures that have occurred in fixed wing and rotary wing, and this is outdated by 18 years, but it just gives you a feel for the failure modes and failure initiation points that you could have. And typically stress concentration is an area that is common for failures to occur. Failure modes can also be identified based on the design and past experience. And the source was from the Aerospace Engine Design book. And I'll be going into parts, different parts an aircraft, launch vehicle, and spacecraft have, and how those are related to the kinds of failure modes you can see. But the point I want to make is that you can identify failure modes based on the design and past experience. For example, you could have blades, and we know blades are rotating at high speeds. Well, if blades are rotating at high speeds, then high cycle fatigue could be a problem, or erosion is a problem. So you can use parts and past experience to drive the understanding of the failure modes that need to be considered in the design process. And I'll cover this into more detail in the future. So what is material overload in metals? The strength of the material is exceeded. That's the bottom line. Anytime you exceed the strength of the material, we call that material overload. And it can occur due to poorly understood environments or undersized parts due to manufacturing errors. Here on the right-hand side, we have many pieces that failed, and these pieces came from a single component. This is more akin to a brittle failure. On the very left-hand side, I have large deformation occurring with a clean crack. In this scenario, we call this a ductile failure. In here, in the left-hand side, I'm covering ductile failures. In the next column over, I'm covering brittle failures. And you can see that the failure characteristics for ductile failure are significantly different from a brittle failure. The brittle failure If you have tensile loading conditions, you have more of a flaw with very little deformation of the structure. In a ductile failure, you can get a lot of necking, and you're going to have a changing characteristics of the cross section. Transverse shear failures in a brittle material are going to typically occur at a 45-degree angle, like glass or concrete. While if you're looking at a highly ductile material under torsion or shear, you're going to see a straight plane most of the time, with a lot of deformations on the free surfaces of that material. And you can also have bending failure, and typically with bending failure, you also see a difference in characteristics. And the source for these pictures and images are provided on the right-hand side. Strength of the material is typically exceeded. That's what material overload in metals means. But I want to show you what that looks like when you're looking at a stress strain curve. Here, I'm plotting the force versus strain. And the bottom line is that when you apply a load and you have almost no nonlinearity, and failure happens, typically that failure is a brittle failure. And it occurs usually when you have fast loading conditions. And the brittle failures are going to exhibit an intergranular or transgranular facets on the fracture surface. Ductile failure typically occurs with slow load application, but it can also occur at fast loading applications. The important thing here to note is that when the loading to the sample, and here we're plotting load versus strain, when loading to the sample occurs, you could have significant amount of nonlinear behavior beyond the yield point of the material, which is the onset of plastic deformation. And that's going to cause significant amount of nonlinearity, which means that the more nonlinearity you have, the more ductile the response is, and the more strain energy under the curve, and the more advantages you have there for crash worthiness protection for an aircraft, for example. And so I want to point out that brittle failures can be a problem because you don't have a lot of notice when they happen. As you can see here, like glass, it will just fail and you're done. Well, with ductile materials, you do have a little bit of wiggle room and maybe even some signs that this could happen before it actually happens. Let me cover now low cycle fatigue. Low cycle fatigue is damage that's related to stress cycles that lead to component failure in less than 10,000 cycles. So in essence, and low cycle fatigue failures basically that's repetitive damage. You're basically applying repetitive cycles at very high amount of loading condition, and that high loading condition will cause failure at low number of cycles. In part 2 of this course, and there are YouTube video lectures below that you can follow, we cover how to predict low cycle fatigue failures, but we will not be covering how to do that in this course, in this particular lecture. But if you're interested, you can go ahead and look at lectures on that in my YouTube channel. High cycle fatigue is damage that occurs at low amplitude cycles typically, usually driven by vibration. And it takes usually millions of cycles for failure to occur. So yeah, big difference between low cycle fatigue and high cycle fatigue. Low cycle fatigue, you have some plasticity involved that really accelerates that failure. You know, just take it as an example, a little wire, aluminum wire, and you bend it back and forth quite dramatically to cause plastic deformation. Well, in those scenarios, you're going to have some amount of damage that's getting accumulated, and failure will occur fairly imminently below 10,000 cycles. While high cycle fatigue is more of a silent killer because you may not see any plastic deformation yet, dislocations and damage are occurring at the micro level until crack will just initiate at some point and start propagating either catastrophically or in a stable manner or is completely arrested. Stress rupture is another fatal mode, and it occurs when you're applying loading to a structure at an elevated temperature for a long period of time. And this rupture occurs, and that's basically what you got. Crack propagation life, this is cyclic loading of a component where crack, there's an initial crack in the system. And the initial crack grows over the life of the part to critical level, and then it propagates unstably. Creep is permanent deformation that occurs as a result of prolonged application of stress. So you have this part, and the part has loading conditions but apply for a long period of time, and temperature usually makes it worse. That applied stress is below a level that will expect to cause plastic deformation. Creep will occur also at temperatures, like I said, that are high relative to the melting point of the material. So anyway, creep can happen, and usually it's one of those failure modes that is ignored. And I invite you to really pay attention to that particular failure mode because it is ignored. And it is ignored often. And I'll be paying attention to that today with examples I'll be providing because it is a painful failure mode that gets often forgotten, and it has caused some massive failures. Here I have the example of fatigue example, and earlier in the chat I saw a comment about the Havilland Comet with square windows. Well, guess what? This particular comet experienced 13 fatal crashes, and over 426 people's lives were taken. And really, the stress concentrations were the cause for these fatigue crack initiations at the square-shaped windows, which then propagated and resulted in greater stresses across the rest of the fuselage and led to a failure event. Crack propagation life is an example where a crack initiation can occur and propagate over the life of the program. And here we use damage tolerance and in my book I discuss this as a terminology that is used. It's a structural philosophy that recognizes that you're going to have undetected metallurgic defects or manufacturing flaws or damage in the body of the structure, particularly at process-sensitive areas such as welds, castings, and you could even have crack initiation points starting from tears, nicks, laps, burrs. Those can progress to a failure at some point. Here in the bottom left, I have an example of a crack in the weld area, or a root crack, or on a crack in the heat affected zone, or also what we call a toe crack. Well, these cracks may not be detectable by the NDE, the non-destructive evaluation techniques that are typically used for detecting this kind of damage. And so one approach that's used in industry is to assume a flaw in the form of a crack of minimum detectable flaws, right? So say the smallest flaw I can inspect is 0.04 inches or 40 tau or 40 mil. That 0.040 inch, if that's the lowest I ever can detect, then sometimes what is done is that you do a crack growth analysis starting with that 40 mil flaw. Even though your structure doesn't have that flaw, it's conservative to assume that if I have an inspection technique that can inspect for that, that is conservative then to do an analysis, assume that every part has a flaw of that amount. We also have mental fatigue fracture failure. I'll show that example later. But let me show you an image from my book and show you what's going on here. What is the philosophy used? We have damage in the y-axis. In the x-axis, I have the number of hours of flight. And what I'm looking for here is the damage as a function of time, number of cycles. And you can see the damage will start at some point, and it will grow to some level. But that damage may not be detectable. And I don't want any of that damage, and I don't want any of those flaws to become catastrophic. So I want those flaws to grow slowly. And that's how the structures are designed. When a structure experiences its flaws are growing, the load is distributed appropriately, and it reaches a level where now the damage can be seen. And I want to be able to inspect a little bit beyond that. And I want to inspect it, and I want to have an inspection technique that's quite reliable, that has the ability to detect flaws with what I call a 90-95 POD, a probability of detection of 90% with a lower confidence bound of 95%. So out of 100 samples, I want to be able to detect a flaw of that size 90% of the time. And so we want to make sure that the inspection technique you use is able to detect those flaws. And you typically will then, for an aircraft particularly, you're going to then develop inspection intervals. And those inspection intervals will then define when you want to do those inspections. So maybe every 3,000 hours, maybe every 10,000 hours. It depends on the component. Some components require inspection intervals that are shorter than others. For example, landing gear, because of the amount of impact loading it experiences during landing, will require a lower inspection interval than the fuselage. An engine component, such as aircraft blade engine, so the blades of an engine, those get inspected as well regularly, because we don't want to have flaws that initiate at the root of those blades and cause failure. And in essence, what we want to be able to do is to predict that damage growth. We want to define the periods of inspection. We want to make sure we have an inspection technique that's reliable to the levels required by the space agency or the aviation agency. And then you want to be able to manage the structure to come up with repair processes. Because just because you discover damage in an aircraft doesn't mean that you are done with it. Maybe there's ways to repair the structure. But there will be a point at which you may have to retire the aircraft because it can no longer be in service because it will cost too much to repair it and refurbish it. Here's an example of a Hawaiian Airlines application where the whole roof of a fuselage or portion of the roof of the fuselage was lost. In this example, and according to the National Transportation Safety Board, the indications were that pre-existing cracks were found in lap joints of the Station 540 that you see here, and on the side of each rivet holes in body Station 360 over here, butt strap near S7R. So this is the region where we had the issues. All other fractures adjacent to the separation area were typical of overstress application. That tells us that there is something going on here. Per the National Transportation Safety Board, 1989, page 10 of that report, fracture surface in the immediate areas surrounding this separation perimeter were corrosion-free. So that section was corrosion-free. So we know corrosion was not a failure mechanism for this, but perhaps was this pre-existing cracks that grew over time. And so early service history records of the Boeing 737 had revealed that difficulties were encountered during this bonding process. And the problem of bonding degradation was either due to the presence of condensation in the cloth, the screen cloth, or due to premature curing of the bond. The disbonding caused direct transfer of fuselage hoop trusses to the countersunk rivet holes, and then ultimately triggered fatigue crack initiation and propagation. So note that when you have a fuselage like the 737, the circumferential hoop stresses are quite great compared to the longitudinal stresses. And the crack propagation takes place perpendicular to the direction of the hoop stresses. However, in the case of the 737, the fatigue cracks were expected to initiate in the outer layer of the skin and not underlying skin panels. Because over there, we didn't have the countersunk holes. So random cracking of these lap joints were reported by several Boeing 737 users, and the rate of crack propagation was dependent on the degree of disbonding, accumulated full pressure cycles, and environments. So as you can see here, the failure mechanisms are not simple, and these events triggered the aviation authorities to look at potentially reducing the inspection times that were there at that time. We also have the Southwest Airlines Boeing 737 rapid depressurization, which is caused by a rupture in the fuselage. The aircraft had accumulated 48,740 hours of service and 39,701 cycles. What the investigators found was a significant amount of damage to the fuselage of a Southwest Airlines, and the fracture was through the lower skin and connected several rivet holes in the lower row of lap joints. And this is not the only incident. After inspecting other Southwest Airlines, it was found that they also had these flaws. The question is, why Southwest Airlines and not these other airliners? Well, research found that Southwest Airlines' business model uses these aircrafts quite significantly in a single day. So every time it takes off and you land, you have a pressure cycle. Well, that pressure cycle puts stress on the fuselage due to the pressure difference across the fuselage. As you ascend in flight, the outside pressure is low, the inside pressure is highly pressurized to the level that's comfortable for the passengers, and the pressure differential causes a hoop stress and a longitudinal stress. These stresses then put loading conditions into the skin. And so Southwest Airlines business model is to fly quickly many days, many times a day, short trips. And that's how they can make a profit compared to other airliners and also sell the tickets for quite inexpensive. As a consequence, you get many more cycles with the Southwest airliner compared to other airliners, and that's why this failure mode was seen more in the Southwest airliners compared to the other airliners. So I hope that makes sense. And then we have 136 airplanes were actually verified and inspected, and they found 4 of these airplanes with crack indications at a single rivet, and 1 airplane was found to have crack indications as 2 rivets. So these airplanes have accumulated a number of cycles of quite large, and the point I want to make is that if this failure had not occurred and it was not this catastrophic, then it could have been a lot worse. You know, one of the Southwest Airlines aircraft where the engine blade failure occurred, it hit the passenger fuselage and a person got pulled out of the window and that person passed away because of that. Well, this failure could have been quite dramatic and could have resulted in people's lives being lost, like the earlier Aloha Airlines here. And as a consequence, it is good that inspections were performed, and it is good that we found these issues. But this has now also alerted the industry to maybe even reduce inspection times and pay attention to these rivet areas that were being a problem. With that said, and so let's look at creep. Creep is a permanent deformation that occurs when you have stress applied for a long period of time. On the y-axis, I have the creep strain. On the x-axis, I have time. And then you have 3 stress levels. And the higher the stress, the higher the creep rate. And creep rate can occur, which could damage the functional performance of the part. It can cause significant damage to the part. And typically, you have 3 stages in the creep behavior. In the first stage, creep occurs to some level, but then it increases at a constant rate. At that point in time, the creep will accelerate, and we call that stage 3. And that stage 3 is when you have accelerated failure. Temperature also has the effect of increasing the creep rate, and so you can use that fact to accelerate life testing by, say, for example, I want to test a part under 10,000 psi, and I have to test it over 1 year. Well, that's going to be a long time to test that. You could then increase the temperature and test it to then accelerate the test program and still give you the curves you need for design. So then we have The primary creep here, stage 1, is where creep resistance occurs. Then we have the secondary stage where there must be a balance between work hardening and the recovery processes at the micro level. And that will lead you to the minimum constant creep rate that is experienced. We also have the tertiary creep, in which there is an accelerated creep behavior due to accumulated damage. And they can also be seen at high temperatures, as I said. A curve creep rate versus total strain will show the large change in creep rate during the creep test. And the principal deformation process that you're going to see during the creep behavior is slip subgrain formation, grain boundary sliding, and the mechanisms of creep that you're going to see are basically dislocations at the micro level. There is a difference between creep and stress rupture. In creep, the testing measures strain versus time at a constant temperature and load, while stress rupture test measures stress at a given strain, and it measures stress versus time to rupture at a constant temperature. Both approaches have been successfully used to study sustained loading conditions. Relatively low loads and creep rates is what you get for creep testing. In stress rupture, you're looking at higher loads and higher creep rates. The testing for creep test can be longer duration because you have lower loads. So you're looking at 2,000 hours to 10,000 hours, and it doesn't always fracture. For the stress rupture testing, where you're looking at strain application, the testing tends to be shorter duration, less than 1,000 hours, and it always result in a fracture if designed properly. The strain in the creep test is measured accurately using sensitive equipment, and the strains are typically less than 0.5%. In the stress rupture test, you're going to have strains typically up to 50%. Let me give an example of a creep failure mode. On November 10, 2009, the Boeing 737 departed Brisbane Airport, and the aircraft was climbing 24,000 feet, and the flight crew observed abnormal indications associated with the right engine. The aircraft returned to Brisbane, where it landed without further incident. When they disassembled the engine and inspected the engine, and now we're looking at this engine area here, the engine disassembly, looking at the stage 1 low pressure turbine, which has a bunch of blades, when they look in there, they found signs of thermally induced microstructural degradation. And it could have been due to the creep resistance of the alloy, and it resulted in the blades being susceptible to failure by creep rupture. So that's one example where we've seen that. Now, we've seen this also in the rocket engine industry as well, and also spacecraft applications where you're trying to deploy a slat or for a deployable mechanism that's stalled for a long time. Creep can then cause it to not return to the deployed configuration, causing it to the spacecraft not being able to perform properly because the deployed mechanism was hindered by the creep mechanism. Due to sustained loading condition. Creep, creep example number 2 is investigation of an aircraft where titanium bolts failed. And the 3 titanium bolts failed mid-life during service operation. Each of the failed bolts were installed on the landing gear component. A metallurgic failure analysis indicated that the fracture mechanisms it was low temperature creep, possibly resulting from a sustained tension load over a long period of time. Visual inspection revealed ductile fracture morphology with no microscopic deformation or corrosion. For all bolts, fracture occurred close to the root. And you can see that here it was close to the root, first couple of threads, at the first pitches of the threads. And so when they did analysis of the fracture surfaces using scanning electron microscope, also known as SEM, the analysis showed microvoid coalescence. And so that is a sign that there's this creep mechanism that could have occurred. Now, the EDX analysis, energy dispersive X-ray, did not reveal any material deficiency other than this, this other mechanism related to creep. Creep number 3 example is a turbine blade of an aircraft engine. A low pressure turbine blade of an aircraft engine was fractured during ground test run. And so the microstructure of that virgin blade was analyzed to look at what's going on, which was actually made of a high strength nickel alloy. And when they look carefully, there was this triple point creep crack where a crack had initiated on the trailing edge of the blade airfoil near the root region. Now, I want to keep in mind and explain to you that the blade to airfoil designs typically, so this region here where the blade attaches to that ring, they tend to be areas of high stress because of the centrifugal forces and also the thermal behavior and gradients across these systems. And so that produces a sustained loading condition that's perfect for a creep mechanism to set in. One of these cracks then propagated, initiated due to creep, but then propagated due to high cycle fatigue. And the airfoil eventually failed due to overload conditions. So you actually had 3 failure mechanisms. First, the creep behavior initiating that flaw. Second, a high cycle fatigue mechanism, then propagating that flaw. And 3, you had this issue of an overload condition that ended in the failure event. The primary cracking was creep, and the microstructural study was key in trying to identify this failure mode at that particular location. Creep example number 4, I thought was worth to give more examples. A second stage turbine blade also, an initiation of a flaw that was also a triple point flaw. In this case, the flaw finally failed due to low cycle fatigue failure. And so the source for this example is given here at the bottom. I invite you to go ahead and download that particular paper and go through the lessons learned from this particular investigation. We also have examples of melting where the melting temperature of the material had been exceeded, and so it resulted in loss of strength. An example of this application is the defective weld in a combustion chamber of the Mars Global Surveyor main engine which resulted in destruction of the engine within the first few seconds of test. The combustion chamber exceeded the maximum allowable temperature, causing parts to melt. And then you have the situation, why did this happen? It's because the weld material in the joint was circumferential. And this annular weld had some amount of extrusion into the combustion chamber due to that overpenetration of weld. Well, the flow of the boundary layer then interacted with this disturbance of the flow due to this overpenetration of the weld material, which then resulted in high melting temperatures. And so they had to conduct a thorough external and internal inspection of the rocket engine to make sure that there is no issue moving forward when it came to these welds prior to hot fire testing. I'm going to go ahead and cover now thermal shock. Thermal shock is really the process where there is a sudden change in thermal stresses and strains that are significantly large in magnitude, and where the heat flux and the component temperature gradient can change abruptly. And these changes can produce cracks as a result of the rapid change in the temperature. And the stresses that are generated in the thermal shock are much greater than you will find in normal loading cycles, and even greater than the ultimate strength of the material. There are examples. For example, there is the United Flight 585, US Air Flight 427, and the East Wind Flight 517, the three rudder incidents, where the PCU secondary slide jamming and excessive travel of the primary slide resulted in a rudder reversal. The latter did a test that revealed that under certain circumstances, the PCU's dual servo valve could jam and reflect the rudder in the opposite direction of the pilot's input. Later on, the teams of investigators conducted a thermal shock testing, which revealed that the uncommanded rudder movement could be replicated by injecting a cold PCU with hot hydraulic fluid. And so this is a type of thermal shock test, and that resulted in demonstrating that the servo secondary slide became jammed against the servo housing. And that when the secondary slide was jammed, the primary slide will then move into a position that resulted in a rudder movement opposite of the pilot's command. So that's an example of thermal shock environments that can cause structural and functional performance issues in the system. Let me move to a failure mode. Various failure modes are tightly related to environmental controls. Chemical related material issues that will result in a strength reduction. And corrosion is one of the biggest issues that we'll encounter in the aircraft industry in particular. For spacecraft, which are usually stored in very controlled environments, that tends to be less of a problem. For launch vehicles that could be stored in less of a controlled environment or are experiencing launch delays for whatever reason, and they are near salt environments or water environment, you could start getting corrosion events, even in launch vehicles. So what is corrosion? Corrosion is the chemical degradation of metals as a result of a reaction with the environment. It usually results in failure of components when the remaining material cannot support the applied loads, or the corrosion triggers other failure modes. And in these events, corrosion can cause even other failure modes such as fatigue and overload. And the way that can happen is that because corrosion has degraded a portion of the material, the remaining part of the material that has not been affected by corrosion will then have to take the additional load that the corroded material could not take. That shift and redistribution in load then decreases the capability of the undamaged material through fatigue or overload. Uniform corrosion can occur without appreciable localized attack, resulting in uniform thinning. You could also have the situation of pitting corrosion, which is quite often and common in where you have a localized form of an attack to the material, and you get these little pits that develop in the material, causing localized perforation of the material. They're really difficult to detect. Crevice corrosion occurs when the localized changes in the corrosive environment exist, and that leads to an accelerated localized attack. Again, here you have a crevice that's getting quite aggressive in the behavior of that corrosion, and it's getting accelerated in that local area. Galvanic corrosion, on the other hand, is an event that occurs when you have two dissimilar materials that are in indirect electrical contact in a corrosive environment. And that usually results, this galvanic corrosion failure mechanism occurs usually from a poor material selection. We'll be talking about material selection later, and I'll teach you how we can choose materials that are not they're compatible so that this galvanic corrosion failure mode does not show up. Stress corrosion cracking is also another mechanism that's observed quite significantly and can cause a significant degradation in the structural performance in real life. Stress corrosion cracking is a mechanical environmental failure process in which the tensile stress and environmental attack combine to initiate and propagate a fracture. The failure by stress corrosion cracking is frequently caused by simultaneous exposure to an apparently mild chemical environment and to tensile stress well below the yield strength. And so again, stress corrosion cracking, that's basically growth of a crack in a corrosive environment. And it can be a significant issue, especially at elevated temperatures. And these events can occur in ductile metal alloys, typically. And it's important to understand that these events need to be protected against because it's of crucial importance. Only a very small stress concentration can quickly create highly active chemicals that are needed to produce these catastrophic cracking events, which often lead to devastating unexpected failures. So something very important to keep in mind with some metals. Corrosion example number one that I want to discuss is corrosion failure found in the Airbus A320 engine intakes. And the failure here occurred in a dissimilar material joint and is strongly related to the adhesive loss of integrity at very low temperatures. It's a complex failure mechanism where the adhesive ductility reduction, so there's a ductility reduction at the low temperatures, and that promoted the microcracks formation within the adhesive layer of the bonded joints. And that in turn sparked this corrosion process because the microcracks within the adhesive allowed the infiltration of dust, moisture, contaminants, and salt water in the interface between the adhesive and adherents, which promoted the creation of a dielectric behavior between the joint adherents, and consequently, it led to galvanic corrosion. So galvanic corrosion is frequent when you have these type of materials interacting in a environment. And so again, it's very important to understand that while galvanic corrosion may not require special conditions, it is of quite importance to understand that damage can occur locally when you have two materials that are not really compatible um, in terms of electrical compatibility. And we'll be talking about that later on how to come up with materials that are compatible. Corrosion example number two, what we're talking about here is an upper surface wing panel that contains an access door, and that was subjected to a detailed metallurgic examination after corrosion was found during a scheduled service inspection. The thing I want to point out is that pilots very often walk around the airplane, and they do that before every flight. And the purpose there is to look for any signs of damage or any issues that look out of order relative to hardware, relative to the position of the control surfaces, and corrosion could be one of those material issues that can be found during the scheduled or unscheduled service inspections. In this case, it was a service schedule inspection. The panel and door were manufactured from an aluminum alloy plate to which aluminum cut for securing the door in the closed position were attached. And so examination of the inner surface showed extensive exfoliation corrosion on both the panel and the door catch positions, and cracking appeared to emanate from the catch position. And that was also observed in other areas of the aircraft, such as the stiffening ribs. So exfoliation corrosion really occurs in materials that are susceptible to this type of corrosion when attack takes place along selected grain boundaries, especially if you're really talking about relatively thin materials. Let me move to a different type of chemical interaction with materials that can lead to a decrease in strength capability or fatigue capability. Hydrogen embrittlement is one such corrosive, or not corrosive environment, but another chemical environment that could be of potential concern. Hydrogen embrittlement is a failure process that results from the retention or absorption of hydrogen in metals, usually in combination with applied tensile or residual stresses. And so it is more frequently seen in high-strength steels. For aircraft components, the common source of hydrogen embrittlement is hydrogen absorption during the manufacturing process. And that's quite interesting, and it has been seen in 2024 aircraft aluminum alloy, as an example. There's been evidence that corrosion-induced hydrogen embrittlement can happen, and that it can degrade the properties quite extensively. In the example I want to provide now, a cadmium-plated high-strength steel bolt from an aircraft flap control unit fractured in the threaded region of the shank near the shoulder. Materials checks showed that the bolt conformed to the required specs. So the ultimate strength of that bolt was just fine. There's no issues there. The fracture surface of the failed bolt was examined using SEM, which I already covered what SEM is, but it's a way of looking at the fracture surface more carefully. And the outer circumference exhibited intergranular features, which suggested embrittlement. So anytime you see intergranular features, embrittlement comes to mind. The embrittlement process in this case was attributed to the cadmium plating, which is applied to the bolts to provide corrosion protection to the steel. So that's something that's done very often. So notice how we're trying to protect the material for one scenario, which in this case is corrosion, yet is this very same protection that's been applied that causes other failure mode, which is hydrogen embrittlement. So hydrogen embrittlement is evolved during the plating process. And in this situation, it became absorbed into the steel. And so the cation plating acts as a barrier to hydrogen diffusion at ambient temperature so that the hydrogen then becomes trapped in the steel. So this is very interesting because in this case, we're protecting this particular steel for a corrosion environment by applying this cation plating. But that process involves hydrogen, and the hydrogen gets trapped now inside the steel by this very cation plating. So very interesting scenario. To overcome this problem, high-strength steel fasteners, which have been cation plated, are now baked at 205 degrees to allow the hydrogen to escape. And so in essence, what happened here, the root cause is very simple. Failure of the bolts was caused by insufficient baking after plating, which then led to the hydrogen being trapped, which then led for the hydrogen to combine with the high tensile loadings that you could have to produce cracking that then got accelerated due to the hydrogen embrittlement process. There are other metallic failure modes that have less to do with the chemical environment, but they have more to do with continuous usage. And so wear is such one mechanism that occurs in screws, in bearings, in gears, but wear is the damaging and gradual removal of deformation of material at solid surfaces. Causes of wear can be mechanical or chemical, erosion or corrosion. And the study of wear and related processes, in this case, is referred to tribology. Well, we do have examples of wear causing significant incidents in the aircraft industry. Alaska Airlines Flight 261 is the horizontal stabilizer jack screw was basically subjected to this type of wear event. The National Transportation Safety Board at the time determined that inadequate maintenance led to the excessive wear and eventual failure of a critical flight control system during flight. And so the probable cause was stated to be a loss of airplane pitch control, which then that resulted from the in-flight failure of the horizontal stabilizer trim system, jack screw, assemblies, nut threads. And the thread failure was really caused by the excessive wear resulting from Alaska Airlines' insufficient lubrication of jack screw assembly. So that insufficient lubrication led to that accelerated wear that then was the very root cause of the issue that was seen, which is the loss of airplane pitch control from the in-flight failure of the horizontal stabilizer trim system. And so that's just one example. There are many examples in recorded and reported examples of wear being a problem, particularly the ball bearings, gears, and other moving parts. Typically, moving parts will be the ones affected by this wear mechanism. So in summary, what we really have, and I borrow this chart, but in summary, what we really have is a number of material failure mechanisms. And these examples I've provided really apply to the area of metals for the most part. And metals exhibit failures that can be quite damaging. You could have elastic deformation that for brittle material, that's all you need and you have failure, or the elastic deformation could be a problem from the functional performance standpoint, meaning the deformations could be too large for the system to operate properly, perhaps through an interference event. Plastic deformation is another failure mechanism, and with repetitive loading, you can get fatigue failure and fractures when you have a flaw that could initiate and propagate. Creep is when you have sustained loading conditions, and then you could also have situations where you have microstructural changes. And I didn't discuss this, but for example, plasticity can cause grain changes within the material, and a coarser grain generally leads to lower properties and more brittle behaviors and less resistance to crack growth. You could also have chemical or electrochemical degradation such as corrosion, and we discussed that. We discussed hydrogen embrittlement. I didn't cover oxidation, but that's another failure mechanism or another material degradation mechanism you could have, which could then degrade the local properties, which can then degrade or can reduce the capacity of the untouched or the virgin material. Physical degradation that we're discussing here, we covered one is wear, but you could have erosion as well. Let's discuss some system level failure modes. And when I cover system failure modes, what I'm really looking at is from the top level view. What are the main failure mechanisms that should be considered in the design of aircraft, spacecraft, and launch vehicles that may not be attached to a particular failure mode, but they tend to be failure modes associated with system level failure modes. And so the five that we're going to discuss today, the four we're going to discuss today, I've repeated distortions, but the four we're going to discuss today is buckling and crippling, bonded joints, fastened joints, and distortions. So what is buckling? Buckling is a structural failure due to excessive deflections, and it produces loss of structural stiffness due to imposed loads. Buckling is a process where when you subject the structure to loads, it cannot withstand the loads with the original geometry. So the structure has to change shape and find a new way of taking those loads. There's several possible outcomes. You can structurally displace the structure to the point that you lose structural or functional performance. There could be large deflections that may induce plasticity, and that can be a problem if you have repetitive loading, for example. Or buckling can cause rupture, which could be a problem. And the structure may or may not be catastrophic, so it could be benign. It could be a benign event. An example I provide here is a business jet hawker, which clearly shows a shear buckle. And the thing I want to point out here is that this looks a lot more like a wrinkle. And anytime you see something that looks like a wrinkle, it's typically driven by a shear loading event. You're usually going to have a lower carrying capacity near cutouts, which may be the reason why you didn't see this mechanism in the acreage region of the fuselage. You could also have buckling events that can degrade the capacity of our structural design, particularly cylinders in launch vehicle designs, and they're driven by imperfections in the shell. So any small imperfection in a shell, thin shell, can cause a significant degradation in strength because that imperfection then becomes a weak point, and so when loading is applied, that imperfection gets pronounced and it grows in size before actual buckling occurs. I invite you to read NASA SP 8007 and also research the NASA NESC 8007 SP release, which is not released yet, but I invite you to look at some research that the NASA community has done recently to better understand the effects of imperfections on the buckling capability of cylinders. Very interesting application. I also check out, I have a YouTube video that goes into the buckling and the finite element analysis of these structures. Here is a buckling event looking into the inside of the aircraft. And you can see in this case that there's buckling that occurs in the panel. But there are some cases where buckling can cause excessive deformation of the stiffening elements. In this case, these are stiffening elements. These are circumferential stiffeners, and these ones are stringers that run along the length of the vehicle. Usually, the skin takes the shear loading, while the stringers take bending moment and take other loads that have to do with axial loads. An aircraft is subject, and you're going to see that later, aircraft are subject to torsion, bending moment, shear loads. And so the shear loading in this case caused the skins to fail in shear or buckle in shear, may I say. And sometimes that starts with the stringer also weakening. But you know, those events can occur and need to be analyzed for. Crippling and buckling is something you can protect against. If you do sufficient testing and sufficient analysis, you should be able to achieve a design that's fairly robust to the buckling failure mechanism. The crippling failure mode is a failure mode where, for example, I have this stringer or this stiffener, and is more of a local failure mode to the stiffener, which may not cause the whole structure to lose load at once, but it's a local failure of the stiffener. You can see that here, how the portions of this stiffener in this example, this I-beam, the shells that make up the web and the flanges, that those are exhibiting a large deflections and loss of stiffness. And this behavior is really called crippling, and it is preferable over having a total failure mode that could cause the structure to collapse. Because this failure mode, when this failure mode is occurring while this is attached to a shell, for example, is not as catastrophic. However, an event like this can start initiating events on the shell and weaken the shell to the point that it will also buckle, and maybe that will lead to a global buckling behavior. Crippling failure modes need to be really paid attention to. It is sometimes ignored because people are really focusing on buckling of the larger structure, but people do miss the point that crippling could be a mechanism that causes these other global failure modes to occur. So very important to understand buckling, crippling, or instability failure modes. Bonded joints are typically used in aircraft applications, launch vehicles, and spacecraft because they actually are good at saving weight. You can see here I don't have to put a bolt on. I have a part that comes in and is bonded with an adhesive. And that adhesive is usually strong, but not as strong as a bolt, for example. But it can carry quite a bit of load. And that loading condition can be such that it transfers the loads through the bonded joint, through this interface. In this case, you could have various failure modes. System failure modes that could occur is failure outside of the joint. That's one example. You could have failure within the metal or the composite. In this case, it's a composite failure. I'll cover composites a little bit later and show you what we're talking about there. You could have a cohesive failure mode where the failure happens within the adhesive, and it usually occurs as a shear load. You could also have voids within the adhesive that could then serve as stress concentrators, and these stress concentrations can then precipitate the shear failure mechanism. You also have cohesive failure mode, where there's a peel loading condition from the edge that could also cause failure. And then you have the interfacial failure mode, which is just between the bond and the adherent. And usually that occurs when you have poor surface preparation, contamination events, and things of that nature. And this is your peel failure mode. So on the right, what you're looking at is peel failure modes. On the left, you're looking at shear failure modes. But they manifest themselves a little bit differently when you look at the failure mechanisms of bonded joints. Here is the desired failure mode that we would like to have. Failure, if you design a system so that the failure occurs outside of the joint, that's preferable. You typically don't want to have failures within the joint because that's less predictable. The better I can design the joint and allow it to fail outside of the joint, that is the best choice you could have for a given design. We also have various failure mechanisms for bolted joints, and here are some pictures of the various failure mechanisms. I'll walk you through some of them. And bolted joints are advantageous over bonded joints in the sense that bonded joints, once you bond structures together, they're sort of permanent. You can dissolve the adhesive using some treatments, but it's not simple. And with bolted joints, the ability to disassemble make them a good choice. The problem with bolted joints is that they can add significant weight to the system. And so for that reason, there's a trade space between bolted joints and bonded joints that you will see in designs. Another thing about bonded joints is that bonded joints tend to be workmanship sensitive. And I have a whole video in YouTube of adhesively bonded joints, which is not part of this course, but if you're interested in speeding ahead and learning more about that, you can go ahead and look at that one. Bolted joints, I also have a video on that you can go through. This subject by itself is a very long topic, but I do want to cover the types of failure modes that bolted joints can experience. Bolted joints can experience bearing failure mode. And what is bearing failure mode? Bearing failure mode is a failure mode where the bolt is pushing against the material surrounding that bolt, and the bolt is reacting the forces, the external loads. And so the bolt is pushing against this material, and the material ahead of the hole is getting compressed. And that compressive behavior is decreasing the properties of the metal, which causes the hole to elongate, and that elongation in turn causes the joint to start losing stiffness, and then that can lead to other problems such as more bolt bending and separation and other things. Net section failure is a clear failure mode where the section fails. I mean, that's fairly out. It fractures. You could also have a situation of a shear out failure mode where a section parallel to the loading action causes the bolt to snap out with some material here ahead of that bolt. You also have a cleavage failure mode, which is very similar to the shear out failure mode, and that's basically a crack event, initiation event that occurs at the hole. You also have cleavage tension failure, which again, crack initiations that turn into another plane that's perpendicular to the loading direction. There's also the bolt failure mode, so the bolts can fail. I didn't cover tearing yet, but tearing is another failure mode. And you could have fastener pull-through, where the nut fails or the threads fail, and you have pull-through of that fastener. I also want to talk about joint separation. That's when the bolt loses, that joint loses preload, and so now the members that are trying to be joined together, there's a gap in between. So now the purpose of the bolted joint, which was to bring to adherence together, that purpose got lost, and that needs to be addressed. And so when you have a gap, you essentially can precipitate a fastener failure mode, or you could have excessive bending of that particular joint. You also have creep and torque relaxation, and creep and torque relaxation can then cause also. What I mean with torque relaxation, so when you have a bolt under preload, and the preload is applied over a long period of time, years maybe, that preload will start reducing over time, and that reduces because of torque relaxation, and plus the material could start creeping, the bolt shank, and so those two things together can then cause a preload loss, which then causes a significant issue with the gapping that we discussed and other things like that. And that gapping then leads to other issues such as excessive bending or bolt failure. Distortions is another area I would like to cover. So you have to ensure that the optics of the spacecraft can produce accurate measurements. And so distortions happens in a lot of areas, but one area that's worth really talking about is, your optics instrumentation can be quite affected by the thermal effects. And so what people sometimes do with spacecraft is an analysis called the stop analysis. You do a structural, thermal, and optical analysis. You start with the thermal analysis, analyzing the spacecraft as it is exposed to on-orbit environments, hot and cold. And that analysis, which is quite complex because it takes into account the radiation, heat effects, the cold effects, and it has to also model the orbits. This thermal analysis produces a number of load cases. These load cases are then mapped into a thermal structural model, and the structural model, which may not be the same finite element mesh as a thermal model, so that causes a problem in trying to map a thermal model result into a structural model because the mesh may be different. That structural model is then ran in a structural finite element package to come up with the displacements at every node. And here, the area of interest is to determine the displacements at the area where we have the optics. In that area that we have the optics, we want to then determine the pointing errors caused by these distortions. And these optical models are then used to understand the performance of the optics. And this process is actually very involved and complex, but it needs to be done because you don't want to fabricate and manufacture and design and deploy a spacecraft that's very costly only to find out that the optics are not working properly. A significant area of concern and an area that a lot of research is going into to really find ways of achieving better ways of doing this kind of analysis. But that is the failure mode we're talking about. If the distortions from the thermal environments are too severe, the optics, the functional performance can get affected quite significantly, which then means that, in this case, distortions is a cause for a problem. You also have CTE distortion. You could have a situation where a bonded joint, one that's metal and one is composites. In this case, I have a metal here, say, and I have a composite and a lower adherent. This composite is going to have a very low coefficient of thermal expansion. The metal could have a higher coefficient of thermal expansion. When this joint is subjected to very hot temperatures or very cold temperatures, then the difference mismatch, that mismatch in coefficient of thermal expansion is going to produce large stresses in that bond line. Thus, large stresses in that bond line could then initiate a flaw, which could lead to failure propagation. This issue, particularly the CTE, could be a significant issue when it comes to spacecraft applications, where spacecraft, usually use bonded joints, but they're also exposed to on-orbit temperatures that are quite extreme in the hot and cold side. And both of those extremes can be a problem. And so usually materials with low coefficient of thermal expansion are usually sought. We're looking at materials that are less sensitive to temperature changes, and they're highly sought, and they're usually used in precision instruments, microscope, flexible electronics, spacecraft, thermal actuators, and MEMS. Low CTE materials also play a crucial role in aerospace components, such as space-based mirrors, satellite antennas. They're built on Earth but operate out in the outer space environment where the wider temperature swings may cause undesirable changes in shape and shrinkage. So a lot of people do work to look at new materials. Invar here and other metallic alloy provide an optimal coefficient of thermal expansion that reduces these kinds of issues. You can also tailor the coefficient of thermal expansion to minimize the effects for the whole range of temperatures. Let's cover composite failure modes. There's a whole course in composites, but in this aircraft structures course, we're trying to understand the composite failure modes, as you need to be aware of this type of failure modes, and you have to design against these failure modes. Composite materials are really good materials because they have the ability of reducing the weight while increasing strength performance. However, composite materials comes with their own problems. Composite materials are manufacturing sensitive, and they're a little bit more complicated to analyze compared to metals, where metals are typically isotropic materials. Composite materials are not isotropic, meaning the properties depend on the direction that you test them. And so that really makes the analysis complicated. The manufacturing is more complicated, but they do have the benefits of the weight reduction and high strength. You could have two types of composites. One is a woven ply, and the other kind is a unidirectional ply. In a more advanced composite materials course, we will cover the types of woven composites you could have. There's a plain weave where you have fibers, the toes going one up and one down, or the 8 harness where you have the two directions are different in terms of how they're weaved together. Unidirectional plies is where the fibers are only in one direction, as opposed to woven ply where you have weaving of fibers in both directions. You can then construct a composite laminate with one or more of these plies, and the way you do that is you lay up the composite together and you bake it in the oven. In the composites course, we then cover the layup process and what it takes to make the composites. But for now, I think the important thing to understand is the basic idea of how what are composites and how they're quickly made, but nothing in too much detail. I do want to cover the types of failure modes that you may see when it comes to composites. And composites are extensively used now in the spacecraft, launch vehicle, and aircraft applications. And composite sandwich structures is one sandwich structure is one structure that's used quite significantly because it can improve the bending resistance by simply putting the composite face sheets apart and creating the space in between and filling it up with a lightweight material like core, foam core in this case, aluminum core. I think the important thing to point out here is that the space in between is filled in now with a very weak material, and the core takes the majority of the shear load while the face sheets take the membrane loads. And together with the core being that thick, what it does, it increases the bending resistance. If you recall from mechanics of material, the bending stiffness EI, basically the E is the modulus of the material, and I is the second moment of inertia. And the second moment of inertia for a cross section that's rectangular, which is 1 over 12 BH cubed, H is the thickness. As you increase that thickness H by double, it increases that moment of inertia by 8 times, 2 cubed. And as a consequence, the bending stiffness goes up by 8 times, which means that I have a more robust structure that can resist bending. And if I didn't have that core and I brought the facies together without the core, then the bending resistance is much lower. Foam core and aluminum core are two types of core that could be used. There are many other cores that have been proposed in the literature. I invite you to take a look at the literature and even pause the video now and check it out. But I think these are areas that you can kind of see what's going on with these sandwich structures. So again, two types of structures. One is a laminated composite structure. Another one is a sandwich structures. Both are used quite significantly. Composite sandwich structures are quite beneficial for resisting buckling, and they're really good for rudders as an example. Rudder is one area where these are used. While the composite laminated approach could be used for the fuselage, for example, as the fuselage in this case only has to take, for the most part, shear loading, in-plane shear loading, and has to take the pressure differential across the skin of the aircraft as it ascends to space. Let's look at the sandwich structure construction a little bit more carefully. The sandwich construction here I have foam and here I have honeycomb. This photo is courtesy of NASA. At the top, I have the top face sheet. Then in between, I have a film adhesive that bonds the face sheet into that core. And then I have a film adhesive again, followed by the bottom face sheet. And you can select materials based on the density you want for the core. And the density can vary for both foam core and aluminum core. The fiber and resin materials could be changed and apply layup stacking sequence. And stacking sequence here means that I could lay up various ply angles to get the tailored properties. And then the film adhesive can be placed in between. So again, I teach the composites course as a follow-up to this course. And so I'm just introducing you to the ideas. The equations that are covered in the previous lecture, stress, strain, constitutive law, and all of that, forms the backbone of the composites course, because there you have to analyze ply angles, and we need to learn about orientations and transformations of ply angles. So that's where that becomes beneficial. But just wanted to point out the importance of understanding the basics in the previous lectures and the introduction to composites here. Although here the goal for me is to teach you the failure modes when it comes to composites. So what are the types of composite defects you could have? There are many of them. You could have fibers that are wrinkles. The wrinkled fibers can degrade the strength properties. You could have waviness of the fiber system, misalignment of the fibers. And you can have areas where you have less fibers than you had desired. That also decreases the strength of the composite. You could have porosity and voids within the composite. And too much porosity and voids, basically within the resin, can lead to a strength reduction, because those are stress concentrations. And the stress concentrations will then be crack initiators to micro cracks, which I'll cover very soon. You could also have local resin-rich areas. And in these cases, now you have less fibers in those areas, which means that that's what I mean with fiber-starved. But those resin-rich areas can then be a initiation point for failure. You could also have flaws, and the flaws can lie between two plies. So ply 1 and ply 2, and these are supposed to be bonded together. Well, you could have somebody leaves a piece of paper or something, like FOD, foreign object debris, and now I have a defect between the two plies, and that could be a significant problem in the design of composite materials. Ply that are incorrect. For example, I want a ply angle to be 45 degrees, but then the ply angle that was put in was 25 degrees. That's the wrong ply. Wrong materials, incorrect orientation, or missing plies. I was supposed to have 5 plies, but I missed 1. And these are not very obvious things to find. When you make a composite to try to find whether you had the correct ply angles, that could be a tough order because it's not always obvious. It's not very easy to find. Sometimes there's programs that will find this late in the game after the testing is completed, and when the test failure occurs, and you look back retroactively, you find that the ply angles were wrong. You have materials that are missing, or the material was the wrong one. Other composite defects have more to do with machining holes. For example, you can have oversized holes, mislocated and repaired holes, and out of round holes. Fasteners can also exhibit failures. I discussed some of those earlier. And then you can have thickness deviations. For example, this was supposed to be 0.8 inches, 0.08 inches, but then it turned out to be 0.06 inches, or something like that. This also happens in bonded joints. You're supposed to control the bond line thickness, and perhaps the bond line thickness was affected by thickness deviations. So these are some areas that we need to pay careful attention to, because composite defects then form the basis for the failure modes that you may later see. And all these composite defects are basically initiators, or the reasons for the initiators of new failure modes that may not have been accounted for, that really need to be looked at quite carefully. So now what we want to talk about is the types of failure modes you can exhibit in the composite failures, the composite structures could exhibit. Fiber breakage is a situation where fibers get broken. And in this case, the failure mechanisms are more complicated than what I'm showing. But in essence, fiber breakage is just fiber failing. You also have the matrix cracking, where matrix could crack through a thickness. And then you have delaminations, which is separation between plies. In this picture, I'm showing other failure mechanisms such as matrix cracking. And by the way, you could have micro cracks that are very small, and these micro cracks could then coalesce to form a bigger flaw that is more visual. And these visual macro cracks could then turn, so this macro crack then turns into a delamination, as you can see here in this picture. And again, delamination, separation between two plies. And your aircraft designs and launch vehicle and spacecraft designs need to be designed to protect against these failure modes. And the list of failure modes is provided here in a list format to show you the kinds of failure modes you could have. And what I'm trying to highlight here is you could have fiber failure in tension, fiber failure in compression. You could also have fiber buckling in compression. So if the fibers lose stability, then fiber buckling could be a significant concern. I also have matrix microcracking, and that can occur both. Microcracking is basically small fissures within the resin. And this, remember, the resin is what impregnates the fibers to give it a shape. Fibers carry the majority of the load in a composite structure, while the resin keeps the shape of the structure and keeps the fibers together. And so if I have micro fissures in the matrix, that might not be a problem. But when they start to coalesce to form a macro crack, then the macro crack could then be initiation points for delamination, or we could have a situation where the fiber detaches from the matrix, or we call this fiber matrix failure or fiber matrix debonding. So the resin or matrix is there really to keep the fibers in place. And so if now I have the fiber detached from the resin, then I'm not really accomplishing the goal. And so things will become weaker in the design. Composite failure modes are quite significant and difficult to address in service. The threat of delamination that arises from in-service loading is one of the primary factors for limiting the adoption of laminated composite materials in the greater volume of primary structures when it comes to aircraft. Now, the launch vehicle industry and spacecraft and aircraft, they have all embraced the use of composite materials. But while they reduce weight and increase the strength performance, and so that strength to weight ratio performance is increased quite significantly, the thing to keep in mind is it comes with baggage. And that baggage is that you're going to now start encountering some complicated failure modes that need to be really addressed early in the design program. You want to really address those early in the design program by doing testing, because you don't want to, as you saw now, two examples I provided so far in this course is the 777X and the 787. Both have significant amount of issues during the test program that cause setbacks. And so why is that? Because the failure mechanisms for composites were not well predicted by analytical models. The analytical models were missing something there, which is the reason why you test. I mean, you should test for a reason, and the testing was useful from that perspective. It exposed new failure modes that were not previously seen. But regardless, you can see how composites does increase the layer. It adds a layer of complexity. That's what it does. Secondly, as you can see, there's a number of composite defects that could then initiate these failure modes, and so now I have complicated the problem even more. So I'm not trying to tell you not to use composite material in your designs, but I'm telling you that this composite materials usage can increase the amount of work when it comes to the design, manufacturing, production, and in-service phase of the program. While typically other damage modes such as matrix cracking can occur first, delamination is really the one that will result in a larger stiffness drop, because if you have a delamination between 2 plies or 3 plies, that will then decrease the bending resistance, or it could also reduce the load bearing capability. In this case, what you see here is some bearing damage, and these delaminations here that are formed does decrease the strength capability and will then cause a more global failure such as fiber failure. Delaminations also are a problem, like I said before. If you left a piece of paper between 2 plies, those are initiation points for failure. But they can also occur from interlaminar stresses that arise from geometric or material discontinuities, particularly from design features such as edges, holes, and drop plies. However, delamination can occur in curved laminates, and they can occur during impact damage events. And so, just to keep in mind, delamination, once it initiates, it will grow under fatigue loading conditions, and then that delamination can continue to grow to the point that accumulates into a structural failure, such as, say, buckling failure or fiber failure. So, ply separation in composites is not to be taken lightly. It can occur between stiffening elements. For example, it could occur between, so say this was a composite, which is not, but it could occur between this stiffening element and the skin, while you may not have bolts, so it will be core cured, meaning bonded to some level, where the resin from the stiffening side and the composite the fuselage side, that skin there, and the stiffening elements, the resin between of the two bond together. They form polymeric links. If you have defects in between, that could be now sources of failure and delamination. A lot of testing is going on in industry to better understand these failure modes. Let me move to composite failure modes as it relates to sandwich structures. You have phase sheet failure, where the phase sheet fails, and that in that case, I'm going back to this kind of failure modes: fiber breakage, matrix cracking, and delamination. So those things can happen within the phase sheet. So again, this is a sandwich structure. This color here, which is yellowish, is a core. And so you could have core shear failure, which is cracking through the core in shear. You could have phase wrinkling and core crushing, which could occur from, and I'll go through that later, but you could have phase sheet wrinkling and core crushing. And then you can have a delamination between the core and phase sheet. And under compression loads, then you will then have this phase sheet pop like a blister. And so that's a delamination event that needs to be considered in the design. You also have shear crimpling, where it's a situation where you have this initially starts straight, but due to misalignments, you can start to have deviations in the load. And so there's an eccentricity between this line of action and this line of action, then causes things to go haywire and a crack is formed. You also have phase sheet dimpling and intercellular buckling. And in these scenarios, you have honeycomb core, so the cells of the honeycomb core and the phase sheet that goes on top of it, the areas that are not supported by the core beneath, that phase sheet now will buckle because it doesn't have enough support. And that happens with large cell sizes, so low density core can be an issue. And here's an example of core shear failure during a test. And then I have the phase sheet failure mode and core crushing due to bending load. And that phase sheet here, you can see quite significant amount of damage. Composite sandwich failure modes, there's a number of failure modes that are due to the global loading of the sandwich structure. They appear together with deformation patterns that are directly related to the global or overall response. And let me go through phase sheet fractures. So that's the one I covered earlier. It could be either compression or tension. So I'm covering this guy right here. And this can be caused by insufficient panel thickness. It can cause by facing thickness or low strength or too high of a load. Core shear failure usually is caused by insufficient core strength. So this core has too low of a strength. Another issue is that these cores can absorb moisture if it's foam, and that will decrease the strength. Or this core is honeycomb, and the honeycomb material could be corroded, for example. So then the corrosion can then cause a degradation properties, which then can cause core shear failure. You can also have a general type buckling instability, where the panel thickness is not sufficient, the core shear rigidity is not sufficient. So combined, you could get a lower buckling capability. I already covered buckling earlier, but it's something to keep in mind. Shear crimping sometimes occurs as part of buckling, and it is caused usually by low core shear modulus and low adhesive shear strength. In addition to the global failure modes, you could have the phase sheet wrinkling behaviors, and these are more like local failure modes. So these were more global failure modes, and now I'm looking at more local failure modes, and phase sheet wrinkling is this one right here. And in this case, a sandwich phase sheet buckles with a short wave, and a local buckling pattern forms. And this local buckling pattern can crush the composite, and can cause a problem. Intracellular buckling is the one I just discussed earlier, is also local. It's this one right here. And that happens when you have large core cells and the area that's unsupported by the core, so that fascia that's not supported by the core will then buckle locally, and that can cause failure by propagating to adjacent cells, and that can cause fascial wrinkling as well. So this could be connected sometimes. Local indentation can occur also when you have either an impact damage event or the fascial wrinkle pushes the core in to the core, causing some damage. There are also, for composites, joint failure modes that need to be accounted for. For example, you could have a situation where you have a bypass stress, so there's stress in the skin. You have a bearing stress where you have a fastener going through this pressurized system. And so now in combination, not only you have the bolt pushing against the composite, you have the far field stress applying tension to the composite. These events can cause failure modes that are quite complicated to analyze and design for. And so yeah, these are additional failure modes that I had not discussed earlier when I covered bolted joints, but they need to be taken into account. And so here I have an example of bypass strength versus bearing strength. And here what you see is what's going to happen when I have a bypass strength failure dominated event. So when I have low bypass stress, then and I have high loading in the skin, so the skin behavior is dominating, the bearing loading is small. In those scenarios, the failure is going to follow an envelope where the failure mechanism is a net section failure mode, where you have a failure across perpendicular to the loading environment. And that really occurs when you have low bearing stress. But and the y-axis here is bypass strength, the x-axis bearing stress, and the curve I'm showing here is the bypass strength bearing strength interaction. So if the bypass stress or the skin stress and the bearing stress, which is a load that the bolt applies onto the composite, if that combination of loads passes or it's outside of this red envelope, you get failure. So that's what this red line is. And so if I'm along this red line above, you get net section failure. And there's a point at which if the bearing stress is too high, that then the mechanism switches to bearing strength failure. And in those cases, what you get is a compression failure just ahead of the hole, which causes a hole elongation. And if you have a hole elongation, that hole elongation is going to cause potential problems, excessive bending in the joint, loss of stiffness, and other consequential failure modes that could be a problem. In a given design, these are special failure modes that should be accounted for, especially launch vehicles and aircraft. An example of a situation where this is involved, not exactly, but is involved, is the AA587 accident composite lug failure. This composite lug failed due to overload. This American Airlines Flight 587 vertical stabilizer exhibited failure November 2001. And that was a pretty catastrophic event shortly after 9/11. And it was an event that had people concerned because it was one of the second deadliest aviation accidents in the U.S. history, where many people died. Over 250 people died. The investigation was quite complicated because initially there's confusion as to whether the terrorism that had occurred months before was involved. But analysis and investigation of this event showed that there was this Airbus, right? So this Airbus, this is an Airbus basically that took off shortly after Japan Airlines Boeing 747-400 using the same runway. And the issue was is this Airbus was flying in the wake of this larger jet. What happens with large jets is that they produce a wake or an area of turbulent air. And so when the Airbus was caught in this turbulent air, the officer, the first officer, tried to stabilize the aircraft by putting in rudder inputs. And so the force of that air flowing against the moving rudder started to stress out the vertical stabilizer. And at some point, the vertical stabilizer snapped off, which then caused the structure to lose stability. And the NTSB at the time concluded that there was enormous amount of stress being put into vertical stabilizer, and they really put the onus on the first officer, saying that it was unnecessary and excessive to put those rudder inputs, and it was not really the wake turbulence of 747 that caused this fatal event. There are things that need to be kept in mind is that the designers did allow for these inputs to occur. And so in some ways one could argue that the design allowed for pilot inputs that should not have happened in the first place. So yes, there was corrective action on how to approach this in the future, but there is also concern on this vertical stabilizer. Now, the vertical stabilizer is connected. So this is a rudder assembly, the vertical stabilizer assembly, which is really connected to the fuselage with 6 attachment points. And each point has 2 sets of attachment points. Each point has an attachment point, one made of composite materials, another one is aluminum, and they're all connected by these titanium bolts. And the damage analysis, composite damage analysis that was performed, it showed that the bolts and aluminum were intact, that the failure should not have happened there, but not necessarily the composite lugs. And so these coupled with 2 events earlier in the life of the aircraft, because they found there's delamination in part of the vertical stabilizer prior to the delivery. And I mean, another point is that there was an encounter with heavy turbulence in 1994, which caused an investigator to really examine the composites. So there was something earlier in this composites also due to this turbulence event. So there is this possibility that the composite materials may not have been as strong as initially known, and so when you have these events combined, it could be a problem. And so they did perform a lot of tests, and it was carried out on these vertical stabilizers, and they found the strength of the composite had not been compromised. And the NTSB concluded that the material had failed because it had been stretched beyond the design limit. But again, the design did allow for those inputs. So that's something to keep in mind. Another point I want to make is that extensive analysis was performed by NASA, and I'm going to point you to that paper. But it is important to note that here the blame was placed on the pilots. And so there is this race of who is to blame, right? So you have the 747 wake turbulence. You have the aircraft flying on that wake of that turbulence. You have the pilot putting inputs that are potentially harming, but that the design allowed. And then you have these delaminations that could have resulted in a decrease in capability. While testing did not show a problem, there is that question of of could have that contributed in any way. So I'm not trying to refute the report, but there are some questions surrounding this that do deserve some merit in looking at. Another point I want to make is that the officers' actions did produce a large amount of load into the force, into the rudder, and it sounds incredible, but that force was close to 203,000 pounds. 203,000 pounds. And it's quite incredible because that's quite large of a load, and it means that the vertical stabilizer did not fail until far in excess of the 100,000 pounds force defined by the design envelope. So while the vertical stabilizer was determined to be consistent with design specification, it is something to keep in mind that this, there was failure here, and the design did allow it. Um, the Pilot Association did argue that the unusual sensitivity of the rudder mechanism amounted to design flaw that Airbus should have communicated to airliners. And so there's also that there's this talk, there's this uh, between the pilots. Anytime there's an accident, you're gonna see these disagreements between the airliners, pilots, and the NTSB, but everybody's really trying to reach to the right conclusion. And there are reports that there have been 10 incidents in which these A300 tail fins had been stretched beyond the design limitations. So this is not the first time this happened. And in some ways, you're going to see the tug of war that requires some thoughts to think about. The NTSB determined that the probable cause of this accident was in-flight separation of the vertical stabilizer as a result of the loads beyond ultimate design. And they're really placing the blame on the pilots because the first officer then unnecessarily put the inputs in. But the reality is that the design did allow that to put in. So a lot of testing was done on this. Recall, one of the things I want to mention is that the A300 was one of the first airliners to have a composite fin. And so that's something to keep in mind. I will invite you to look over this particular report that won the best paper. This paper was written by Raju Gaskin, Mason Krishnamurthy, and Carlos Davila, and they work at the NASA Langley Research Center. And the title of this AIAA piece of work is called the NASA Structural Analysis Report on the American Airlines Flight 587 Accident, Local Analysis of the Right Rear Lug. And so an analysis was performed by NASA to try to understand what happened here. And they're doing as part of the National Transportation Safety Board failure investigation of the accident. And what they're trying to do is evaluate the loads experienced by the right rear lug using a global local analysis procedure. And they use progressive failure analysis trying to simulate the failure mechanisms. And they were trying to then also look at loadings that were performed during the certification testing in 1985. They were able to produce with excellent agreement, the failure modes and the location of failure using this advanced modeling. After they anchored the models with the 1985 test, then they used the analysis to analyze the component level testing conducted by Airbus in 2003, later on as part of this investigation. They also found there an excellent agreement between the analysis and the observed failure modes. From the analysis, they concluded that they were able to then be able to show that the modeling is capable of predicting the cleavage type failure modes that we're seeing, and that the loads applied in during the failure event were 2 times the limit load of the lugs as is described in the accident report. You also have other failure mechanisms that have caused rudder failures, and those are delaminations, flaws between the core and the face sheet. And what I want to describe here is situations where when you have a honeycomb core with say a core system where air can be inside that core. When you manufacture an aircraft on the ground, you could entrap air at 14.7 psi inside, or 1 atmosphere, right? But when the aircraft ascends to space, to 40,000 feet, and climbs to that altitude, and you have a defect in place, the air outside has decreased, yet the air inside of the composite could become entrapped. And so that difference through the thickness in pressure can then cause a face sheet to blister and blow apart. And there are several incidents in the launch vehicle, spacecraft, and aircraft applications where this has happened. For example, on March 6, 2005, an Airbus 310 experienced a rudder failure that had a stress fracture in the tail that went unnoticed for several flights prior to the incident flight. And the A310 does not have that mechanism in the tail that will then suspend the growth of fracture inspection program of composite rudders as inadequate. And so we also have 5 cases of partial rudder loss in Concorde aircraft, and not a typical Concorde, but the rudder failed due to a debond between the aluminum honeycomb and aluminum skin. What is interesting here is that there's corrosion involved on the inner skin surface, and the British Air Accident Investigation found that the debond actually was growing slowly over time, and then it rapidly increased in size until failure. So this is not, they could not detect this, and it was a significant issue. And it was related to this idea that core can get entrapped in the core and is not able to escape, and a defect between the face sheet and the core could then be subjected to loading environments that cause the face sheet to blow apart. Let's cover the idea of impact damage, a very important idea that requires careful attention, as impact damage is one of those events that is one reason why composite materials can be quite challenging in application. Now, impact damage can also occur in metals. The good news is with metals, we can see what impact damage has done. You will see it in the form of nicks, dents, damage. While there's a certain amount of impact damage that could occur in composites and silently cause damage within the composite that may not be visually seen. Lightning damage, bird strike damage, hail damage are things that we can see. Tool drops may or may not be able to see. And the good news is that we try to implement impact damage protection plans for composites. I'm going to have you look at that more carefully as part of your research. Let's look at low versus high velocity impact, because it does play a role into what you can actually see versus what you cannot see. So if you have low velocity impact at moderate speeds, so you may have like that'll be like handling incidents, dropping a tool during assembly or maintenance. So those are just few examples. Low velocity impact may be hard to visualize or to be able to see, yet it could reduce the strength of the composite quite significantly. Say I have a tool drop here on the composites, creates a delamination. Now this composite is now subject to compression loading. Well, this delamination now is a source of weakness and can cause the composite to fail. High energy impact at high speeds could also occur. The high energy impact at high speeds could cause hail damage. And this could also happen with small stones or in the runway that then get kicked up and then they hit the composite and they can hit the aircraft. High energy impact at very high speed can be a problem, and that can happen with spacecraft applications such as in orbit debris and meteorites. And so those are areas that need to be kept close attention because they can affect the spacecraft performance. Hail damage, lightning damage, it can actually puncture the composite, as you can see here, can chip away to the composite. It can cause a cleavage failure mode. It can actually, it will just look like this, for example. So the fish is basically lifted out completely. And you could also have other types of damage. Like drilling the fasteners can cause delamination. You can over torque the fasteners and cause crushing of the sandwich structure or laminate fiber damage or foreign object debris left behind. Now, this is not impact damage necessarily, but you could consider drilling and torque as a type of handling damage. Not exactly quite impact damage, but it is something to keep in mind. Tool drop during processing of the vehicle. You could also have inadvertent contact with ground equipment, such as a ladder or platform contact, slip and contact with railing due to improper installation. And here, an example of this is there was a few incidents where a catering company came in and contacted an aircraft. And that contact event caused, so that catering company is trying to deliver food to the aircraft. And so that catering truck basically hit the aircraft at low speeds, but at high energy did cause some damage to the stiffening elements of the composite system. And so that's an example of something that could happen that may not be visually seen until there is some rattling going on during flight. Rough handling during transportation can occur as well. And then hail damage. During transportation, you could transport a launch vehicle in a truck or a spacecraft or some materials or some components for an aircraft even are transported in airplanes. And those transportation events are going to be it's going to subject the hardware to environments that can cause failure or damage of the structure. So damaging composite materials. A large undetected manufacturing defect could occur, and it could be a problem. So we could also see surface scratches from damage, impact damage, where the length and depth of the scratch is defined, and the orientation location is assumed to be most critical. So these things can happen and should be looked at. You could have this idea of undetected damage, and that's the one that concerns every composites expert, is that you could have a damaged area that's consistent with almost something that you cannot see, but almost something you cannot see that could be critical. And that could be a problem because composites in general are dark in color, and so it's hard to see damage in them. Undetected impact damage is one of the most serious types of flaws you may see for many composite structures, and the main aim is to really reduce the use. Is really to reduce maintenance by using analysis and testing to demonstrate that the damage does not amount to a safety risk over the design life of the structure. Now, an aircraft exposed to environments for many years, 30 years, you can expect that at some point impact damage events will occur. And so that's looked at closely. Inspections are done over time by defining those inspection intervals. But most importantly, you have repair approaches. Repairs can be done to basically look at fixing those areas where delaminations occurred or fiber failure occurred. Fiber failure is hard to really detect through non-destructive evaluation, where delamination is a little bit easier to examine. I do have a YouTube video lecture on repair processes that's worth watching. One of the things you want to do is you want to define the threats for each structure. Damages from manufacturing, accidental damage from assembly and handling, accidental damage from in-service operation. And the way you want to do that, you already know that hail damage is one of them. You know that a catering truck could hit the composite aircraft. And so you can characterize the types of threats you may see, tool drops and things like that, to then use those as guidance to then design composites and perform testing. And the next step is really to define the modes of damage for each threat, which could include delamination, puncture, crush core, and many others. So for each mode of damage, there's characteristics such as initial flaw size, threshold of detectability, critical flaw sizes, and the growth of damage, impact damage, is really characterized by periods of little or no growth. It's possible at low loads. And then it could suddenly start growing quickly at relatively high loads. So you definitely want to pay attention to this, to the impact damage events, and making sure that for each damage mode that we're characterizing the flaw sizes and the threshold of detectability. A significant effect of impact damage is a significant reduction in static strength once the impact has occurred, and often the most critical damage is induced by a low velocity impact event. As that's not visually seen, it causes delamination, and that reduces the bending stiffness. Here's an example of the kinds of failure modes you can have in sandwich structures. Here's a type 1 damage where it's a local damage. The face sheet is damaged, so you have delaminations, matrix cracking, or fiber failure, but nothing has happened to the core. A type 2 damage approach, and this came from a book, is to look at the disbond between the core and the outer skin. So this kind of defect could be a problem when the composite is under compression loading. You also have the type 3 damage where you have a cracked core due to an impact damage event, and then a type 4 where you have this core crushing event, as you can see here. You can also, sometimes you can have access from the outside, so you can inspect from the outside, but you cannot access the inside. And so if there's any amount of impact damage that occurred here that you cannot see from the other side, that could be a problem. That hidden event could pose significant amount of problems that are highly concerning. Generally, type 1 really accompanies one of the other types of failure. So here you have compression loading that cause core crushing. And sometimes you have delamination failure events that can propagate all the way through a thickness in a pyramid shape. And so the damage in the outside could look minimal, but when you look beneath, it's quite propagated. So how do you deal with that? How do you deal with a situation where an aircraft was known to be subject to impact damage? Now, to fix that, or to replace a wing or replace large components, could be millions of dollars. Is there something we can do in the labs to reproduce the testing environments and fully understand whether that impact damage event is a problem? And that's where testing analysis can be very valuable in saving money, but also can be quite dangerous, because if you don't understand the impact damage events sufficiently, perhaps the impact damage events are assessed to be benign, but yet they're quite not quite benign. There could be a problem instead. So the type of damage and extent of damage depends on a lot of different factors. The materials that you use, like Kevlar, is a good fiber system because it can resist impact damage quite significantly, which is why it's used in law reinforcement, for example, enforcement for bullet protection, as an example. Materials can selection, like material systems like fiber, resin, the core system, all that can influence the extent of damage, and it does depend on other factors such as the stacking sequence, thickness, lip. If you have a very thick lip, perhaps that's a good thing. When it comes to composites, sometimes when you design them, you put in something called sacrificial layers, so that if the layers in the outside get damaged, you don't take a penalty hit. You don't have to even repair in some cases, although you should for cosmetic reasons, and also you don't want initiation of flaws in those areas. So sometimes repairs are done by cutting out those areas and performing a repair. And the structural configuration matter, whether you have a ramp, the stiffener type, the boundary conditions, where you have a curved panel versus flat panel. And then the impactor shape matters, the energy, the mass, the size, the stiffness, and the angle of impact. And, so there's a lot of factors here playing a role that all of this makes really analyzing impact damage quite complicated. I invite you to pause the video, download these two documents. One is called the Impact Damage Resistance of Composite Fuselage Structures, and the other one is called the Review of Damage Tolerance for Composite Sandwich Airframe Structures. These two articles are extremely valuable, and I recommend reading them to understand better how impact damage resistance is really looked at from the composite fuselage perspective. You can use coatings to really detect damage. The damage indicators are very useful. If you have paint and you see a scuff mark, you know something happened there. External insulation also. If I have cork and the cork is dented, I know something happened there, and I can examine it more. I can try to reproduce those environments in the labs. External coatings can also pose impediment to characterize impact damage. So yes, while they could be indicators, they can also be on your way of really looking at what's going on beneath. And so this kind of cork or paint will require removing them to then look at what's going on. Another thing is that the cork paint, also cork foam or external insulation, these protective devices for thermal protection in most cases, this could actually make situation worse by distributing the load over a wider area and causing more widespread damage. What I'm showing here is damage threshold. In the y-axis, and there's a lot of curves and a lot of things going on, so let's take it step by step. So in the y-axis, I have the damage size area. In the x-axis, I have the impact energy. So the higher the impact energy, and I don't care what mass you use, the damage size is going to increase. So with impact energy increase, the damage size increases. And so the other thing I want to point out here is that there's a certain level of damage. If it's beneath that area of damage, you may not be able to see. So let's call this the damage detection threshold. And the thing here is that you have low mass, medium mass, high mass, and different velocities of impact. The higher the velocity of impact, the higher the mass, the higher the energy, impact energy, and so the higher the damage size. And so the lower the velocity with the high mass, the lower the damage size, and the lower the velocity even more, the lower the damage size. And so the thing I want to point out is that velocity and mass both contribute to the impact energy level, 1/2 mv squared, mass times velocity squared, and that correlates directly to an increase in damage size. But if the impact energy is low enough, there is the potential where you may not see the damage because the damage is just beneath the damage threshold area. And so that can be a problem. And if you translated this, there could be situations right in that edge where the residual strength capability could be quite degraded. And you can see here in the y-axis residual capability, in the x-axis damage size, and for different impactor events, you can see that you could have different residual strength capability. The larger the damage size, the lower the residual strength capability, but there is a damage size at which you can detect by NDI. There is a damage size where you can no longer see. And the idea here is any visual damage where you start to see any visual damage, I want to have the ability to have residual capability. And you want to have enough residual capability to not have a catastrophic failure event in flight. There will be a point in time where visual damage is useful, but I want to be able to be here if I can. No residual strength decrease, that damage area here, and I'd rather have that point correlating to this dash line. I want to be able to detect any damage before it becomes too of a problem. Because if it's not visible and I have a huge amount of residual strength decrease, I could have a catastrophic failure in flight. And here I'm showing the impact energies, and this comes from paper AAA 98 1784, influence of impactor mass on the damage characteristics and failure strength of laminated composite plates. And what I show here is the damage area, impact energy increase, the damage increases. And you can see here that as the mass increases, the damage area becomes higher. You could also see then this correlates straight to the compression failure load with the lower the impact damage energy. So say take this point, which is almost no damage area, you get a high compression load capability. But as the impact energy is increased and the damage area is increased, then now you start to have a decrease in load carrying capacity, which means that compared to a pristine situation where there's no failure, there's a significant amount of strength degradation. In other words, higher energy of impact, higher the damage that you're going to get, the larger the damage size you're going to get, and the larger the damage size you're going to get corresponds directly to a decrease in load carrying capacity of that composite structure. And again, picture perspective, what I don't want to have is a hidden failure becoming a problem when it comes to load carrying capacity. Because we know that those events can happen from tool drops and things like that. Impact damage is typically unsymmetrical, so it does need an understanding of the progression of damage and residual strength. Damage tolerance of sandwich structures is more complex than laminated composites because now you have additional failure modes that need to be accounted for. Core crushing, face sheet to core bonding. I discussed that, the bonding. Typical impact damage is not uniform through the thickness of the sandwich structure or even a laminate, since the impact or impactor or projectile can penetrate or damage the outward facing skin, while the inner skin may remain damaged, or vice versa, the area where the impact event occurs, that area may not show much, but then the opposite side where the impact did not happen, the opposite side of the impact surface, that surface is much more damaged. So what I'm talking about here is this area here is impacted. Not much damage can be seen here, but more damage is seen on the other side. So those are scenarios that could happen and have happened. And so what we want to make sure is that visual inspections for damage, we want to find those indicators. And we want to implement impact damage protection plans to reduce impact damage events on composites because of the issues we discussed. And again, it becomes more difficult because the core can mask damage or hinder effectiveness of non-destructive evaluation techniques. There's this handling damage, and I got this from the open literature. There's a composite failure in a Delta II side rocket motor, and right now, so far, it has been attributed in the open literature by potential damage from the supports in a new transportation system that was used at the time. And following the failure, they revised that new transportation system, and they came up with better ultrasound inspections of the boosters to ensure this composite failure did not occur. In fact, you can watch a YouTube video, but basically during flight, moments after launch, the side rocket motor failed, and this GPS satellite was lost. Here are lightning damage events are quite visual. They're not always visual. We do have a lot of incidents when it comes to lightning damage every year, not causing a crash necessarily, but causing quite a bit of damage that causes repairs and, in some cases, even having to retire the aircraft due to the amount of damage. Here you see the entry point of the lightning, and here you see the exit point of the lightning. And this looks like hail damage, but it was a lightning event as well. So for that reason, aircraft are designed to dissipate the electrical energy from lightning strike back into the atmosphere with little effect on the aircraft and none to the passengers. When lightning strikes a plane, it tends to hit an extremity, like a wing or nose, and then it will run along the exterior skin of the plane before exiting to another extremity via specifically designed static dischargers. Aircraft has also incorporated lightning protection, and they show by analysis and tests that the structure can dissipate the static electrical discharges, and they also provide necessary electromagnetic protection and provide acceptable means of diverting electrical current arising from lightning strike so that the vehicle is not endangered. For launch vehicles, lightning protection is also used so that the lightning does not impact the spacecraft launch vehicles. And the day of launch, they also ensure that lightning is not occurring within a radius of particular size. And if they're happening, that you don't launch that day because you don't want lightning to strike the launch vehicle. There are test and inspection procedures that have been implemented over the years to ensure satisfactory maintenance of these lightning protection systems. And while I'm discussing impact damage, lightning could be considered a type of impact damage event, although it's almost like a super high velocity event, but it's more of a thermal event combined with impact event. Here is an example of the some ground equipment hitting the composite, and so you could have the ground vehicles and ground service equipments hitting the composite at low velocity, but this is high mass, so it could be a problem, and it's a blunt impact as well. And you could have high velocity hail impact. And the Professor Kim at University of California, San Diego, has done tremendous amount of testing of hail impact events in composites. We also have Dr. Reimer has done significant amount of testing in that area, and there's publications about this out there. Fiber metal laminates do offer advantages when it comes to composites in terms of damage tolerance and fire resistance and impact resistance. They've simulated hail impact on glare, which is a glass reinforced aluminum laminate, and they could only see visibly dents. So here's a glare with an ice mass ball of 90 grams, and there's a dent of 10 millimeters. And it's very similar to aluminum 2024, not too different. With glare, again, 1 millimeter depth. So with composites, you will see much more damage, but fiber metal laminates is one approach being used to resist hail damage. Now, the guidelines from the FAA state that above 23,000 feet, all radar echoes must be avoided by more than 20 miles. And you want to detour around a storm on the downside should be avoided, since the wind is likely to carry the hail to the downwind side. And so, you know, I'm pretty sure pilots would love to fly through some turbulence because it's exciting, but you don't fly through a pretty significant thunderstorm because you could get damage onto the aircraft as seen by the hail damage I showed you and the lightning damage. And so there are reasons why we keep away from thunderstorms. Usually safe to land even after hail impact or lightning damage, but um, passenger safety is always number one. But also here the real issue is the cost of repair and the cost of having to deal with an issue when you could have avoided it by flying around the storm. Hail will generally strike the crown, other horizontal surfaces. I'll show a picture later. Laminate thickness is the determinant factor for the indentation caused by hail impact. You increase the laminate thickness, reduce the indentation of damage created by the hail impact, while higher fiber volumes reduce internal damage for thin gauge laminates. So there's trades that can be done to come up with optimal plies, optimal thickness, optimal materials to minimize hail impact damage. And again, here's more pictures. Here's a windshield in this case, the sandwich structure where the radar is located at the nose. And here's another example, and then here's another example. Impact damage can occur on aircraft structure from a variety of different objects. And I already went through that. The range in summary can be due to low velocity, high mass impact caused by baggage handling vehicles, and dropped equipment during maintenance to high velocity, lightweight, hail impact, and runway debris. A significant impact event can occur on the fuselage while heavy equipment is being mounted to the aircraft. And that happens. Impact damage caused by hail has been known to cripple a fleet. Thus, recently, American Airlines had 80 airplanes removed from service as a result of hail damage at Dallas-Fort Worth Airport. And it has been reported that over more than 100 aircraft were damaged by baseball-sized hail damage, causing over 500 flight cancellations. A lot of money spent in trying to fix these airplanes, repair them. And although baseball-sized hail is not a common occurrence, an understanding of the effect and detectability of this type of damage in solid laminates can help engineers determine what to do, what course of action to take, COAs take to address these damage events. So let's look at some pictures I took from an FAA report, which I'll be showing you at the end of this article, this presentation. But I hope you're enjoying the fact that, and appreciating the fact that failure modes in aerospace applications, particularly aerospace applications, is not straightforward. And the failure modes are quite significant. And here is an example of the things that can happen. The cockpit, you could have bird strike damage. You could have hail damage. And here's calculations that people have done of the kinds of joules, energy joules you could get due to various loading conditions. In the case of the hail impact damage, the hail also disintegrates, so there's a limit of how much the hail can really do, how much hail the damage can really do to the composite. You also have tool drop damage. People have done calculations on things that can happen. Bird strike is really a high number of joules compared to hail damage. And you could have damage into the engines and so forth. So people will characterize these threats like in a threat assessment diagram, determine, okay, in the wing area, I expect falling tools with this amount of energy. Lifting equipment, I'm going to have this amount of energy. On the lower windskin, I could have falling tools or hail impact and things like that. And you can characterize the types of threats you could have. And when you're mounting parts and things like that, that can also cause impact energies. And so all this stuff is very useful because now you can take this data and size your composites and your structures to, and it doesn't have to be composite, it can be metals, but you can size your structures to try to account for these failure modes. The other point I want to make is that as you increase the velocity of impact, you start with delaminations. Then you go to backside fiber failure with minor delamination. So that means that the front side that got damaged, not only that front side got damaged, but the backside, which may not be inspectable, gets damaged. And you could then have through the thickness cracks with delaminations going all the way through, diamond-shaped patterns. And there is a point where with higher energies, the no penetration phase, so there's no penetration to the other side, so it hasn't gone through like a bullet. But there's a point in time where you start to get extensive through the thickness cracks, and then you get a clean hole when the energies are quite high. Here, I'm showing you when barely visible impact damage could occur, so it stops about here, and then from there I have visible impact damage from there on. I do have recommended reading for you, and I would like to do research. I would like you to pause this video and do research on this and kind of meditate about what is discussed. But in this report, detection characterization of hail impact damage in carbon fiber aircraft structures is going to give you an appreciation for aerospace design. And the conclusion of today's lecture, I want to bring you back to what we're trying to do. We're trying to come up with philosophies, analysis approaches, and test approaches that can help you design aerospace structures, whether it's a launch vehicle, spacecraft, or aircraft. And what we're trying to do is ensure that these structures are robust to a number of failure modes, both in the metal and composites arena, and also they're robust to many different environments. And as you can see, those failure modes are not complex. A lot of things need to be considered. And so that brings me back to lecture 1 on systems engineering, which is to really pay attention to the details, to really work with other design team, with other teams like the manufacturing team, the materials team, and all that, because if you select a material that's corrosion sensitive, then you have to really think about that. And so I can go on and on and on, but again, it's very important to really pay attention to failure modes. So I hope you enjoyed today's lecture. We will continue the coverage on aerospace structures coming up. Have a good day.